Let us next see example 1.4. We are nearing the end of this chapter. So what does this example say? The SI unit of energy is joule, kilogram times meter square per second square, that is divided by second square. And the SI unit of speed is meter per second, and that of acceleration is meter per second square. You already know these things. Then, which of the following formulae for kinetic energy given below, that is these 5 formulae, can you rule out on the basis of dimensional analysis? That is, you are going to apply dimensional analysis on each one of them, and you have to decide which one of them can be ruled out simply from dimensional analysis due to the fact that the dimensions on both sides are not matching. So let's see. So you can see the solution on this side. I haven't actually written it as a solution, I am just showing the main calculation of the dimensions of the different quantities involved here in these equations. If you really want to write a solution, you would have to treat them separately. First you take part A, which has this equation, then you write the dimension of kinetic energy is this, and the dimension of the right hand side, which is some other quantity involving mass and speed or velocity, is this. And then you write that because the dimensions do not match, so we can rule this out. It's not a dimensionally consistent equation. But okay, now let us actually see what's going on here. And you may notice one more thing, I have written M prime. I have done this to avoid the confusion between mass M prime. This M prime actually is mass. If I write M, then that would be mass here, but at the same time we have meter here. If you want, you can write M here also, if that does not cause any confusion. So this is the SI unit of energy, kilogram times meter square divided by second square or per second square. So the structure of this unit, which of course is our joule, tells you how kinetic energy is a derived quantity. I mean, how does it come from mass, length and time? And that immediately tells you that the dimension of kinetic energy is this, mL2 t minus 2 or mL square t to the power minus 2. And then what about this other quantity? Here you see that we have the square of mass times the cube of velocity. So because of square of mass, you will have m2 here, and the dimensions of velocity is L t to the power minus 1, but you have the cube of that, so L3 t to the power minus 3. So this is the entire dimension of this quantity, and here, yes, really actually they are not matching, and that is why this first equation can be ruled out simply from dimensional analysis. What about the second one? You have already calculated the dimension of k, so that stays there. What about this 1/2 of m prime times velocity square? 1/2, this 1 divided by 2 is not going to affect anything because it is dimensionless. We already did a similar calculation before. And because you have simply mass, so you are getting m here. But then you have square of velocity. Velocity has dimension L t to the power minus 1. So because of the square, you are getting L2 t to the power minus 2. So yes, they are actually matching in this case, the two dimensions, the two sides. But recall that this alone, this dimensional consistency of this equation alone doesn't tell you that the equation actually is correct. You need to know the physics behind this to say if it is correct. So instead of giving a tick mark, this. Anyway, we do not have to say anything about this, we just have to figure out which ones we can rule out simply from dimensional analysis. Next comes kinetic energy equal to mass times acceleration. A stands for acceleration. So we calculate the dimension of mass times acceleration. For mass we are having m and the dimension of acceleration is Lt to the power minus 2. So that's how you have this dimension of the quantity mass times acceleration. But that does not match with this one. So this one is also dimensionally inconsistent, and that is why it is false. It can also be ruled out. But then next you have this one, where it's almost like this one, only the difference is that here you had 1 over 2, here you are having 3 over 16. But when you calculate the dimension, just like 1 over 2 had no effect on the dimension, 3 over 16 also does not affect the dimension, and you end up having actually the same dimension. So this one also has the potential for becoming an actually physically meaningful equation, although it looks strange because you already know that this is something you have seen in many places, not exactly this, but at this stage we can't say anything more, and we don't have to. And finally you have this equation. For this you already have the dimension, this one, and for m prime a you have this dimension. Now do you recall something from the previous video? We already discussed in that video that you cannot add or subtract physical quantities having different dimensions. For example, in that video we gave the example of distance plus time. That does not make any physical sense. Something similar is happening here. These two quantities have different dimensions. Where is that other one? This. So they cannot be added in the first place. So there itself, this sum itself is meaningless. So it does not go beyond that. So there is no need to check how the dimension of this quantity equals or does not equal the dimension of this, because this quantity is not a physical quantity. It does not have any dimension. Not in the sense that it is dimensionless, but its dimension is not defined at all. So that is why this one is also ruled out. And next let us see how we can use dimensional analysis to actually calculate the form of an equation. And that next one involves simple pendulum. So next we have example 1.5. Consider a simple pendulum. The text writes something else also here, which I haven't written. It describes what a simple pendulum is. But because you already know what it is, so I haven't written that part. Instead, I straight away went to whatever is there next. Suppose that the period of oscillation of the pendulum depends on the pendulum's length L. We will come to all these things, okay. Let me first read. The mass of the bob m and the acceleration due to gravity g. Then we have to derive an equation for its time period, the time period of the pendulum, using the method of dimensions. So this is how a pendulum, a simple pendulum basically looks. This is something rigid to which a string is attached at this end. The other end of the string has this object, which is your bob, and the mass of the bob is m. The length of the pendulum is the length of the string. Well, you may notice one thing, that actually the pendulum length should be length of the string plus the diameter of this sphere if you are having the bob as a sphere or a ball. But two things are being ignored here. The one thing is that the diameter of the bob is so small compared to the length of the string that it is being ignored. It does not really affect the ultimate result that much. And the other thing that is being ignored is that you may notice that we are not talking about the mass of the string. We are only talking about the mass of the bob. That is because the string is so light compared to the bob that we can meaningfully neglect its mass. This type of simplifications are always necessary in science. If you don't do this, if you take every minute detail, everything into account, then the equations that you are going to get from that type of consideration will be so complex that they will be unsolvable. You won't be able to solve them, but then what is their use? So, in every part of not just physics, in the other sciences also you will see simplifications and sometimes drastic simplifications. That's the only way to do science. But anyway, so that's the length and this is the mass of the pendulum. And acceleration due to gravity, of course, we already know what it is. Right now we only need to know that it is acceleration, that's all. And what is time period? Well, what does a pendulum do? It oscillates. How does it oscillate? You grab the bob and draw the pendulum like this on one side and then you release. So the pendulum comes down, goes to the other side due to inertia and then again comes back. Due to gravity, you already know more or less about this process. So it swings back and forth like this. So the moment you are releasing the pendulum and it has just started its journey, the time it takes to again come back to that position from where you released it, that is one oscillation. And that is one oscillation means that act is one oscillation and the time that it takes to make one oscillation is the time period. So let's now see how we can use dimensions to figure out the structure of the formula for the time period in terms of these other things. Alright, so we start our argument by first naming the time period something. Let's call it capital T. Then the fact that T depends only on the length of the pendulum, acceleration due to gravity and mass of the bob tells us that this is how in general T is going to look in terms of those quantities. Here K is a dimensionless constant like those 1 over 2, 3 over 16, that type of thing. And this x, y and z are some exponents, some numbers. Well, this is only a guess, okay, because you may ask what if there is a plus something else, we don't know. Okay, this is something we are guessing. We are guessing that this is how time period is going to depend on length, acceleration due to gravity and mass. And then when we finally figure out something from this guess, we will then have to go back and do experiment and see if our guess is correct. That's a different thing. But now what shall we do after this? Now the only thing we can do is we can calculate dimensions on both sides. If this formula has to be correct, at least it has to be dimensionally correct. Are we going to get something from dimensional consistency? That's what we are going to see. So we take dimension on both sides. The dimension of time period, well, actually we should have called it something else, but in the book it's given as capital T because we also use the capital T symbol to denote dimension of time. But anyway, ultimately you are going to get just this, so no problem. So this is the dimension of time period because it is time after all. that should be equal to the dimension of the right hand side, and you already know that these quantities behave like algebraic symbols. Symbols means variables. So you can calculate their individual dimensions, take their corresponding powers with exponents x, y and z, and then multiply these things, and that will give you this dimension. Because k is dimensionless, so you can just simply forget about it. The dimension of length is L. The dimension of acceleration due to gravity, because it is acceleration, is L t to the power minus 2. But outside we have that y. Do not forget these exponents. Actually, we want to calculate these exponents. We cannot calculate k from dimensional analysis because k is dimensionless. So dimensional analysis is not going to tell us anything about what the value of k is. Okay, so that part will remain k, but we can calculate x, y and z. Next part, the dimension of mass is m. So m, and on top of that you have z. And then again, treating them as algebraic quantities, you write finally this, where we first write m because that's how we write. Okay, so m to the power z. Here you have x and here you have another L with y on top of it. So you are getting L to the power x plus y and time t to the power minus 2y. So these two dimensions are same. So that means on this side you only actually have the time dimension and no other contribution from the other 7 base quantities. Only time is present here. Here, however, you do see mass and length. So that means the contributions of mass and length should be 0. And what are the contributions? The contribution of mass is z and the contribution of length is x plus y. So z and x plus y both have to be 0. And the contribution of time, it should be 1. So minus 2y has to be equal to 1. So now you have ended up getting equations involving these unknown quantities x, y and z. So let's write those equations down and then try to solve them. So dimensional consistency then gives us z equal to 0, x plus y equal to 0 and minus 2y equal to 1. So already you have the value of z, and from this last equation you get y equal to minus 1 divided by 2. And when you use that value in the second equation, you end up getting x equal to 1 divided by 2. So now you are going to put these values back in the original guess, which is this. T equals k times L to the power x, so L to the power 1 over 2 times g to the power y, g to the power minus 1 over 2 times m to the power z, m to the power 0. So you see that actually mass plays no role. And what about this? This is actually square root of L, and this is the reciprocal of the square root of acceleration due to gravity. So that's how a formula comes out for the time period in terms of length and acceleration due to gravity. It turns out from physical experiments that this k is actually equal to 2 pi. And yes, this is how the time period looks. I mean, this actually is the form of the time period of a simple pendulum. That time period equals 2 pi times square root of length divided by acceleration due to gravity. And with this example, this chapter actually ends. Ends not in the sense that it is completely over. There are the exercises next, so that we will start solving from next week. So see you next week with those things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.